Hello and welcome to this video on calculating the differential cross-section for electron-muon scattering in quantum electrodynamics. This is going to be at tree level, so no loops and no renormalization. We don't have to worry about any of that in this particular video. So we're going to be splitting this into two parts. In this first part, we're going to be calculating the amplitude for this process. In the second part, we're going to go ahead and turn that amplitude into a differential cross-section. And I'm going to go ahead and do this hopefully as clear as possible, right? Taking it really slowly, explaining as many steps as I can in detail, but as always, if you have any questions, then please do let me know in the comments and I will try my best to answer. So before we get started, I just wanted to give a quick rundown of the general sort of idea of calculations in quantum electrodynamics and quantum field theories in general. So the idea is we consider some particular process. So in this case, that is going to be electron-muon scattering. We're then going to write down all of the relevant Feynman rules, but of course in practice you'll either just remember all of them or have them all with you. But in this video, I'm just going to sort of worry about the relevant ones for this process, so I don't have to write them all out. We're then going to draw all of the allowed and also specifically topologically distinct Feynman diagrams that contribute to this process. Now, we'll talk a little bit more later in the video about what this actually means to be topologically distinct. And then we're going to go ahead and calculate the amplitudes for each of these diagrams using the Feynman rules. Again, we will see how to do this later in the video. And then we're going to sum the contribution from each diagram to get the full amplitude. And then eventually we're going to turn this amplitude into something that an experimentalist can measure. And in this case, that's going to be the differential cross-section. So I'm going to go ahead and state all of the relevant Feynman rules that we will need to calculate the amplitude for this process. So these Feynman rules can, of course, be derived. And if it's something you haven't done before, then you should go ahead and do this at some point. You can do this in a canonical quantization approach by, considering the interaction terms and the Lagrangian density and the Dyson series and doing Wick contractions and extracting the Feynman rules. And you can also do this in the path integral approach, right? So it's something you should do if you haven't done it before. I'm not going to do it in the video, but if you want to see it at some point, then let me know. But first and foremost, we should talk about the most important rule, which is obviously for the QED vertex. This is the interaction vertex. And QED is a theory of light interacting with charged fermions. So first and foremost, the important thing to know about this vertex is charge must be conserved. Now, as with all vertices in quantum field theories, momentum must be conserved. But also in this case, flavor must be conserved. So what that means is that we can't have electrons becoming muons or anything like that. So if you go ahead and you take a look at our QED interaction vertex, you will see that we have two types of lines. So we have the solid lines with these arrows on them. These are going to go ahead and represent our fermions in our interactions. And these little arrows, what they represent is the direction of charge flow. Okay, so these are spin-and-a-half fermions, so they carry charge. And the direction of these arrows represents the charge flow, and it must flow nicely, right? We don't want to see anything where we have charge coming into a point like this and we have the two arrows flowing against each other. So it must sort of look like a flow where it has a kind of clear direction in which the charge is flowing. So those lines represent our fermions. You can also think of the sort of direction of this flow showing the conserved Noether current for the interaction. So that is just the flow of electric charge in the case of QED. And we also have these other wiggly lines. They represent our photons in our interaction. Now you'll notice that they have a label. So this has a sort of label nu, right? This Greek letter nu. And that's a space-time index label. So the reason why we need this is because photons, they are space-time valued objects, right? So they have a space-time index there. You can think of them as four vectors or one forms. So we need to sort of have a way of representing the information that they carry. But you can also think of this index as really lying at the vertex. You can think of it here. All you really need to know is that the gamma matrix that comes from this QED interaction vertex must have some space-time index, and we can represent that by labeling, either the vertex or sort of, the end of the photon line to show that it carries this particular space-time index. So I wanted to briefly discuss some important things about spinors and Clifford algebras. So we're not going to go into too much detail, but we're going to be working in the Dirac representation of the Clifford algebra for both videos. So our spinors are going to be 4x1 complex vectors, and our gammas are going to be 4x4 matrices. And we're not going to discuss Clifford algebras and their relation to the Lorentz group and spinor reps of the Lorentz group, etc. in this video. We're just going to quote results whenever we need them. But of course, this is important to sort of at least have a basic understanding of at some point if you're trying to do these amplitude calculations. So I would recommend, going away and trying to make sure you can grasp the concepts of these things, just because, it's important to understanding the structure of these particular calculations. So unfortunately, there is this convention that you just have to get used to, that we tend to write space-time indices explicitly. So what this means is that we are working with the components of general space-time tensors explicitly. So whenever you see something like p mu, for example, those are the components of the 4-vector momentum. It's not the object itself, right? It's the components in some particular basis. However, for spinor valued objects, okay, so spinor space objects, like gamma matrices and spinors themselves, we suppress their indices, okay? So rather than working with the components of these objects, we actually work with the objects themselves. Now, the gamma matrices are particularly confusing in this sense because not only are they, a space-time vector. Of course, I'm calling them gamma matrices because they are matrices, they are linear operators in spinor space. So they technically have another pair of indices. So sometimes you see these written as like A, B, like the matrix indices for the gamma matrices. So we suppress these. Now, in practice, what that means is we have to be very careful about how we write things down with objects that are, spinor space objects, essentially, because, we're not just writing down numbers anymore, we're writing down matrices and column vectors and row vectors. So we have to be careful that we're writing these things in the correct order. And we have some rules to help us deal with this. So that can be a little bit confusing when you first see it, but hopefully that's clear. So I'll just sort of show you really now. So this gamma nu, for every value of nu, so nu, it's a space-time index, right? So it runs from 0, 1, 2, 3, and I'm just assuming you have had exposure to special relativity. So, for each value of nu, gamma is a matrix. So for example, gamma 0 is a matrix. In the Dirac representation we're working in, it's a 4x4 matrix. And what that means is, it has indices that represent its rows and its columns, right? So you can write that something like this, okay, where this is the row index and this is the column index. But like I say, we typically suppress these indices. So we don't show these indices explicitly. So something like this is really gamma nu AB. So for each value of nu, it's a matrix with, the row index indicating the position in the row and the column index indicating the position in the column. So now we need some Feynman rules for our fermion lines. Now I should mention that for all of these Feynman rules, what we're going to be doing is essentially multiplying all of the contributions from each of these lines and vertices together. So each line or vertex contributes some factor, and then we're going to multiply these together. But again, because we have spinor valued objects, we need to be careful about how we multiply these things together. And again, we'll see that in a little bit how we do this. So for an incoming fermion, you'll see that we have this line coming in, as we've already seen, but now we've got these labels. So we have the momentum label, and we also have the spin state label. So this is not to be confused with spinor indices, which again are being suppressed here. So the spin state label basically just takes on two values, right? And it shows you, the two different spin states that in this case a spin a half fermion can have, okay? So again, it's needed because we need to show all of the information about the particular incoming or outgoing particle. So we represent that, or that contributes a factor of this U spinor, okay? So it is a positive energy Dirac spinor, so it's a solution to the Dirac equation. And then for an outgoing fermion, it's very similar, but instead of having U, we have U bar, and all this U bar is something called the Dirac adjoint. So you can see it's defined by, we take the Hermitian conjugate of the spinor, and then we multiply on the right-hand side by gamma 0, so the 0 gamma matrix. And again, don't worry too much about, where this is coming from, just take it as a definition for now. We'll use this a little bit more, particularly in the next video when we calculate the differential cross-section. So I just wanted to mention as well, obviously we don't have antifermions in our particular example, so I haven't written the rules down. But the key thing to know about this that might confuse you the first time you see this is, how do I know if something's a fermion or an antifermion if I don't have it labeled explicitly? Well, the key thing is, and also to get the diagrams to be consistent, is we need to have, antifermions where they have the momentum moving in the opposite direction to the charge flow. So if you look at both of these lines that we have here, because they're fermions and not antifermions, the momentum is going in the same direction as the charge flow. But for antifermions, we indicate them by having the momentum going in the opposite direction to the charge flow. Okay, so, I'm always going to be having the momentum flowing in for the incoming and out for the outgoing. So, what that would mean is, I would have for positrons, the flow arrows, the charge arrows would be going against the incoming momentum if they were positrons incoming. But again, we don't need the rules. They use negative energy solutions to the Dirac equation, so you'll see these as V and V bar. But again, we don't need them for this particular example. And so finally, we need our rule for the photon propagator. So this is for any internal photon lines that we're going to have in our diagram. There is also one for internal fermion lines, so a fermion propagator. Again, we don't need it in this particular example. Now, you'll notice here I'm saying in Feynman gauge. What this means is because essentially quantum electrodynamics is a U1 abelian gauge theory, we basically have from the path integral quantization some gauge fixing parameter, right? So this is just something to fix the gauge. This essentially appears if you calculate the propagator in full in the propagator, but Feynman gauge is a choice of this gauge fixing parameter, which basically makes calculations particularly simple, especially for this case, but sometimes you want to choose other gauges to make certain calculations more simple. So this is the particular form of the propagator in this gauge. Of course, you might be thinking, well, how can I have a choice here? Shouldn't that affect the overall answer? And the answer is no. So overall, the full amplitude will be gauge invariant, right? So it won't depend on my choice of this gauge fixing parameter. So you'll notice that this propagator has, the metric components in the numerator. So we're working in the convention here that the metric is, plus minus minus signature. In the denominator, we have this k-squared factor. So again, if you haven't seen this before, we're working with 4 vectors. So k-squared really means I contract 2 4 vectors with the metric as shown. And we have this plus I epsilon factor in the denominator. You will see this in all of the propagators in quantum field theory. This is basically, due to, we want to shift the position of the poles for, when we calculate these propagators, basically to do with complex analysis, right, and how we, obtain these propagators. But actually, because our propagators are never going to go on shell, so what that means is that k squared will, typically when we think about, if you think back to special relativity, we know that we can, when we're setting, and I should say this here, c equal to h bar equal to 1. For all my videos, I'll be doing this. So k squared is equal to m squared, right? So p squared is m squared. But for a photon, obviously, the mass is 0. But it will never go on shell, right? An internal photon will never go on shell. So that means for the internal photon, it doesn't satisfy this relation, right? So it actually doesn't satisfy this, relativistic dispersion relation. And therefore, k squared is never going to be equal to 0, which means that we actually never have a problem of dividing by 0 in the denominator, essentially. So we can actually drop this plus I epsilon factor in the calculations, and you'll see me do this when we go ahead and calculate the amplitude, and you'll see a lot of people do this. But it is there, and you can leave it in if you want to. So now we're going to go ahead and see how we can draw all of the allowed Feynman diagrams that contribute to our electron-muon scattering process at tree level. So we said we wanted to draw topologically distinct Feynman diagrams, and for our purposes this means that we want to draw diagrams that give distinct contributions to the amplitude. And in practice this means that they have different momenta flowing through the internal lines in the diagram, and these internal lines are sometimes called virtual particles. And the reason they have different momenta flowing through these internal lines is due to the different ways that we can connect the external particles together by these interaction vertices. So for 2-to-2 scattering in quantum electrodynamics at tree level, there are only 3 types of topologies that we are going to be interested in, and actually 3 types of possible topologies, and these are the so-called ST and U channel diagrams. And these variables ST and U are called the Mandelstam invariants, and they are the squares of the momenta flowing through the internal lines for each of these different cases of these different topologies. And the reason they're called invariants, right, Mandelstam invariants, is because, well, they're squares of some momenta. So let's look at this in general. So we have something like p squared, right? Well, we know that this is a Lorentz invariant quantity because it has all of its space-time indices fully contracted. So Einstein's summation convention, we're summing over the raised and lower indices here. And so because it has these space-time indices contracted, it is a Lorentz scalar, and therefore it's an invariant quantity, right? It holds in any frame of reference that I choose. Now, of these different Mandelstam invariants, the most kind of intuitive one is the Mandelstam invariant S. And in the center of mass frame or center of momentum frame of the interactions, this is where the incoming particles have equal and opposite 3 momentum. S represents the square of the total center of mass energy, but we will discuss a little bit more about relativistic kinematics of this problem in the next video. So to show these 3 topologies, we're first going to fix the momenta and the positions of these momenta of the incoming and outgoing particles on the page. So what I mean by this is you can see we have the 2 incoming momenta P1 and P2, and I'm fixing it so that P1 is always going to be above P2 in all of the diagrams I'm going to draw. And similarly for the outgoing, I have P3 above P4. And this is actually important to do because if you start sort of changing the relative positions of these momenta on the page, then you're going to get diagrams that you think are new but are actually equivalent to old ones. And we'll see an example of this when we do the sort of physical example that we're interested in. So we can have a look then at our first topology, which is the S-channel diagram. So the S-channel looks something like this. And we can see that we're defining the Mandelstam invariant S to be the square of the momentum flowing through the internal line. So the internal line in this diagram, has this momentum here. So this is our internal line. Okay, it connects the two vertices, and the vertices, the interaction vertices are represented by these little black dots. Okay, so it's indicating that we have a vertex there. Now, how do I know that this is the momentum flowing through this internal line? Well, whenever you're looking at Feynman diagrams, you need to remember that momentum is conserved at each vertex. So what that means in practice is that the momentum in is equal to the momentum out at each vertex. Okay, so if you think about this vertex here, what's happening? Well, we have P1 and P2 going in, right? Look at the directions of the arrows, right? These are going in. And then we have some momentum. Let's say originally we might have called this momentum K here, going out. So we can see that, well, by conserving momentum, so momentum in must equal momentum out, we arrive at, P1 plus P2 is equal to K, right? Because we're labeling K as momentum out. So we can actually just label the momentum out rather than calling it K. It's completely fixed by, whatever the external incoming momenta of the particles are. And of course, it's important to mention that by momentum conservation, so thinking about momentum flowing into this vertex here, we have P1 plus P2 flowing in, we have P3 plus P4 flowing out, and therefore we know that P1 plus P2 is equal to P3 plus P4. But again, this is something you would expect anyway by overall for momentum conservation of the entire process, right? The momentum in equals momentum out for the entire process. So you can equivalently say that S is equal to P3 plus P4 all squared. That is also fine, and sometimes you will see this. So I thought I'd just quickly mention before talking about the T-channel diagram, the reason why these diagrams and these legs of this diagram look different to the QED Feynman rules is because here I don't care about whatever type of particle it is. I'm purely trying to look at the topologies of these different diagrams. So all I care about is the momentum flow. So I'm just representing all the internal and external legs by the same solid line. So there's no charge flow arrows, anything like that. So with this T-channel diagram, you can see that the key thing is that the momentum flowing through the internal line is given by P1 minus P3. Again, you can see this if we think about conservation momentum at this vertex here. So if before I had labeled this on, if I called this momentum generally K, you can see that I have P1 coming in and P3 and K going out. So using my momentum conservation, that tells me that P1 is equal to K plus P3, or equivalently that K is equal to P1 minus P3. Okay, so you can see that must be the momentum in terms of those external momenta that flows through the internal leg of this diagram. Of course, by conserving momentum at this vertex here, that's also equivalent to P4 minus P2. So just check that makes sense to yourself. So you'll see with the Mandelstams, there's always two ways of expressing them in terms of different external momenta that you choose. But I always like to sort of work on this vertex here, so I always label this as P1 minus P3. So the final topology that we have is called the U-channel diagram. Now, the first thing to watch out for and be careful here is that this crossing point here is not an interaction vertex. And you can see that because I've not labeled it with a black dot like I have with the other two interaction vertices. And the reason I've done this and crossed these over and it looks a bit strange is it's just a way of diagrammatically representing that I'm changing which external momenta are connected at a particular vertex. So now at this vertex here, we have P1 and P4 that are connected. Sometimes you might see this drawn, and this is a better way to do this, to be honest, with a little gap like this. And also you might see this drawn in this way, right, to show that they're not actually crossing over. It's not an interaction vertex. Or you can just stick to, like I am here, putting in little dots to show when it is a vertex, and if there's no dot, then it's not an actual vertex. So all this is doing is changing which external momenta are connected at this top vertex and the bottom vertex. And you can see I've, in all of these examples, I've kept the positions of the momenta on the page fixed, right? So I still have P3 above P4, P1 above P2, and then you can see that, that's all that these different topologies are about. And this, these 2-to-2 scatterings is, how can I connect these external momenta differently at these interaction vertices? And that's what gives different distinct contributions, topologically distinct diagrams that are going to contribute to a particular process. And you can see that that's reflected in what momentum flows through the internal line in that particular diagram. So if I start messing around with the relative positions of the internal and external momenta on the page and connecting things up, and I find that I have the same momentum flowing through the internal line in the diagram, then it's just the same contribution, and I've just double counted basically. So you can see that this gives me, by considering momentum conservation at this vertex here, by the same sort of methods we used in the previous two examples, I have that the momentum flowing through is P1 minus P4 now. And again, this defines my Mandelstam invariant U, which is equal to P1 minus P4 all squared. So I thought I'd quickly try and illustrate why it's important to make a choice for the sort of orientation and the layout of the momenta for the incoming and outgoing particles on the page, and then stick with it for all of the diagrams that you're going to try and draw. Because if you suddenly change it midway through, you can see things get a little bit confusing, because, if I sort of swap the P1 and P2 like I have here, and then I thought, okay, well, if I conserve momentum at this vertex, what momentum do I have flowing through this line here? Well, you can see that, I end up with P1 minus P3, just again by the same logic, thinking about the momentum here that are connected to one another. But we've already seen that that actually corresponds to a T-channel diagram in terms of the other, sort of orientation that I started with, and I should have remained fixed. I shouldn't have changed any of this around. So you can see that if I start changing things around, things get confusing, because this looks like a U-channel diagram, but now it has the same momentum flowing through it as the T-channel diagram did, and therefore, these are equivalent in the sense of, really I should have just kept the momentum sort of orientations fixed, and then I wouldn't have this kind of confusing problem where, it looks like a U-channel diagram, but really sort of comparing it to what I've already done, it actually is the same as the T-channel diagram. So now that we've seen all of the different topologies that we might encounter for 2-to-2 scattering at tree level, we're going to go ahead and return to the problem at hand, which is our electron-muon scattering. So we're going to start off as we did when we were looking at those different topologies, by fixing everything in place. So we're going to fix the orientation and the labeling of these external particles on the page. So we have, each fermion is labeled by whatever type of fermion it is, so an electron, and then we have the momenta and the spin label. So the spin labels are the S and the S prime, etc. And then we wish to connect these through allowed interaction vertices to give allowed Feynman diagrams. Okay, so remember, we have to conserve charge, which is really the main important thing for QED at each vertex, but also we can't have any sort of flavor changing vertices either, so flavor must be conserved. And if we try and do this, we get only one valid diagram, and this is the T-channel diagram. So if we come down and have a look, this is the only diagram that we will get. Now, why is this the only diagram that we will get? Well, let's have a look at this. So let's pretend we wanted to draw a different diagram. So I start again with my fixed configuration as above, and maybe you want to try connect these to get a S-channel topology. So something like this. Okay, so I may be labeling a diagram like this, and I add my charge arrows in. Remember, the momenta I'm always drawing as flowing in. So we have a P going in, we have a Q going in, and then we have a P prime going out and a Q prime going out. And then if I add my charge flow labels on, you can see that something weird happens, which we mentioned earlier in the video that we don't want to happen. So again, they are fermions, so the charge arrow goes the same direction as the momentum arrow. And what you can see starts to happen is I either have over here the charge arrows flowing into one another, okay, and that's a bad sign. We want to have this continual clear flow. And then over here I have the charge arrows flowing away from one another, which again is a bad sign. So what's going on is, if you think about this, I have two negatively charged particles, so an electron and a muon, entering this vertex here, but the photon itself doesn't carry charge, right? That's why we have no self-interaction vertices in QED, because you need to have charge for the photon to interact with you. The photon itself doesn't carry any charge, so I have -2 charge coming in but 0 charge coming out, right? So that makes no sense, and therefore this diagram is not allowed, because neither of these vertices conserve charge. And I'll leave it as kind of an exercise to try and do the same thing for a U-channel diagram and see why that particular diagram doesn't work. So let's just quickly take a look at this diagram in a bit more detail and discuss a few of the things that are worth noting. So first things first, you see that I have these space-time indices labeled on the vertex. Now, This isn't always done by authors or in papers, but especially when you're starting out, it's a good thing to do because it helps you remember firstly that you have a gamma matrix essentially sitting at this vertex which carries a space-time index, but it also is going to help you sort of decide what indices to use for the photon propagator, because the photon propagator essentially is going to take you from one index to another. So the indices in the metric and the photon propagator have to match up with the indices that it's going from and to. So we'll talk about that a little bit more in a second when we write down the amplitude. But that's one thing to do. Now you can label them whatever you want, right? It doesn't matter. Just make sure you're not using the same label anywhere. And also you'll notice that we haven't actually labeled the spin state labels on any of these particles. That's just convention. Unfortunately, again, you should know that they're there, right? That each of these particles has its own unique spin state label, which is labeling the spin states of the fermion. But again, these typically aren't included in these diagrams. So this is our only valid diagram, the T-channel diagram. So now we're going to go ahead and use the Feynman rules to calculate the amplitude. So we're going to go ahead and use our Feynman rules to write down the amplitude for this particular Feynman diagram here. So we're going to call the amplitude this curly m. Now, one thing I should say is that within these Feynman rules, there technically is a overall conserving four-dimensional delta function. We're not going to include that in what we're considering the amplitude here, but that always comes along. And if you do the path integral quantization, you'll see this comes from, when you transform to Fourier space from the position space correlation functions. That's the kind of nicest way to see where this comes from. But that always is there for all diagrams, just overall, and it just conserves overall form momentum in the process. So we're going to ignore that. So we start off with, well, in QED, I like to think about, well, how many vertices do I have first? Because if you look back at the Feynman rules, so if you forget any of them when we're doing this, just look back. Each vertex carries a factor of IE along with the gamma matrix. So we have two vertices, therefore we're going to have two factors of IE. So we have an IE squared to start off with. Now, the next thing we said is we need to be very careful about how we do the spinor sort of space object multiplication. And the way to do it is as follows. So, all of these spinners and spinor valued objects, spinor objects, are all going to be, where the fermions are. Okay, so along these lines that have a charge flow. So you want to focus on those, and we're going to multiply the factors going against the direction of the charge flow. So what I'm going to do, picking this flow up here, for example, I'm going to start with multiplying by the U bar spinor for the outgoing fermion. I'm then going to multiply this by the gamma matrix with index rho. And then finally, I'm going to multiply this by the U spinor for the incoming fermion. Okay, so that's going to look something like this. So we're going to have a U bar. And again, that spinor has momentum P prime. Then I have a factor of, the gamma matrix with index rho. And then I have my U for my incoming spinor of momentum P. And then I have another charge flow, right, which is the muon charge flow. So I'm going to do the same thing, and it's going to look pretty much the same, other than the index is going to be different and the momentum labeling is going to be different. So I have a U bar for the outgoing, spinor for the muon that has momentum Q prime. I have a gamma matrix now with index nu, and then I have a incoming spinor momentum Q. And the interesting thing to note about this is, a amplitude in quantum mechanics is a complex number. So there should be no overall kind of spinor structure left. Okay, so if you look at each of these sort of products of three individually, what they are is, it's a 4x1, 1x4 row vector, a 4x4 matrix, and then some column vector, and that is precisely going to give you some complex number. Okay, so each of these sort of products of three are kind of their own sort of distinct product that gives you a complex number. So actually I can move these around. So I can move this around as a 3, because as a 3 it's just a number. I can't move things around on their own, because then I start multiplying matrices and column vectors in weird orders that don't make sense, right? But as a 3 I can move them around. So this could also sit the other side of this. That's completely fine. So what else don't I have? Haven't I included yet? Well, the final thing is I need the photon propagator. Okay, so the photon propagator, again, look back to the Feynman rules, is given by the following expression. So there's a minus I, and then there's the metric components. Now the components of the metric, okay, or the indices, sorry, on the metric are going to be, as I said, related to the indices that you've put on the vertices. So it's like going from rho to nu or nu to rho. The order doesn't matter, because obviously the metric components are symmetric. So I can write this in the following way. I can say eta, let's say rho nu, and then that's in the numerator. And then a denominator, again, we're dropping that factor of the plus I epsilon. So it was k squared, but in this example, the momentum flowing through that line is p minus p prime. So I'm going to write this as p minus p prime all squared. So just a few quick comments about the photon propagator. So you might be wondering, how do I know whether to put the indices on the metric down or up? And you need to remember that, again, the amplitude is a complex number. So once I've computed the full amplitude, which we have done now, there's no more Feynman rules left to apply. So this is the full amplitude. We just haven't simplified it yet. You know, it's a complex number, so there can be no sort of space-time tensorial component structure left, right? It just has to be a complex number. And again, I'm sort of assuming that you've done some special relativity in the past and you're familiar with this. So there can be no space-time indices remaining that are uncontracted, right? So all space-time indices have to be contracted, and you can see that they are, right? We have a row and a nu upstairs and a row and a nu downstairs here. You might be wondering, you know, why did I choose to put the row and nu indices up on the gamma matrix? It's up to you. You can put them down if you like, right? You know, that's completely fine. Then you just have to have both indices up on the metric. So that's the first thing. The second thing is that, remember, because of this weird convention that, you know, has just developed over the years where we write space-time indices explicitly, what this means is that, you know, I can actually write this wherever I want, okay? So if you wanted to put this literally anywhere within this amplitude, that's fine, because, you know, remember, some people sort of tend to think that, you know, okay, this thing is the metric is a matrix, right? And, you know, it is when you write it without the indices, but as soon as you put the indices in, this just represents numbers, right? For each value of rho and nu, this is some number. However, that's different for something like the gamma matrices, because for each value of nu, it is a matrix. So, you know, these are just numbers, so we can just move these wherever we want. But, you know, with the spinor objects, because we don't write those indices explicitly, we have to be careful. So you can write this propagator wherever you want. Another interesting thing is, you know, if you note here, this is precisely equal to t, right? Our Mandelstam invariant, right? P minus p prime squared. Okay, before we had it as p1 minus p3. All right, they're just labels. So here our p1 is now p and our p3 is p prime. And that's nice, right? And this happens a lot in amplitudes. You know, this structure is that you have these invariants appearing, and that's why we give them a name, and kind of makes life a little bit easier, makes the final sort of expressions a little bit neater. So all that's left to do is go ahead and tidy up this final expression. So one thing to note is sometimes you might see this, for example, written as J rho, okay, so some sort of current, and it is precisely that, right? It's the conserved notor current. Once you multiply this by the charge, it's like the electric current. But I'm not going to do that. I'm just going to leave it as is. So we can count the factors of I. So we have, you know, I squared and a minus I. So that gives us a plus I overall. I won't write plus I. I'll just write I. Now, one thing also to note is, you know, we have this this metric here, this eta rho nu. So remember, again, sort of thinking in terms of special relativity now, I can write this as just, you know, for example, eta nu. Gamma nu, right? So I can just, you know, contract those indices and use Einstein's summation convention to write it like this. So that can also simplify what we've got as well. So let's go ahead and do that, you know, whilst we're doing this simplification. So we have an E squared here. We have our currents, so U bar P prime. And again, we are going to contract one of these indices. So we're going to lower this to become an eta with a gamma with a nu downstairs. Too many Greek letters to remember. And then U bar Q prime. This one we left up. Q. And then finally, I'll just fit it in down here using a dot to multiply. So we've used the metric to contract those indices. So all we have is a 1 over t here, right? So we could have really, just at the end, written this entire amplitude over the Mandelstam t. So that is our final amplitude calculation. We have it here. And in the next video, we're going to go ahead and turn this amplitude into a differential cross-section. So this is the second video on calculating the differential cross-section for electron-muon scattering at tree level in quantum electrodynamics. So if you haven't seen the previous video, make sure you go and watch it so you can follow along with this video. So in that video, we used the above Feynman diagram to calculate an expression for the amplitude for this process. So this curly m is our amplitude, and it's given by the expression you can see in front of you. And in this video, we're going to use this amplitude to obtain our differential cross-section. So firstly, what is a differential cross-section? Well, essentially, it just tells you how likely a scattering process is to send particles in a particular direction. And the important thing is that this is something that an experimentalist can measure, and they can do this using a particle detector, something like the Large Hadron Collider, and this is particularly sensitive to the structure of the theory. So, you know, it can sort of give you a clue as to whether your theory is making correct predictions or not. Now, as we know from quantum mechanics, if we want to obtain physically meaningful quantities, we're going to have to work with the square of the amplitude of the particular process that we're interested in. So before we go ahead and give the exact expression for the differential cross-section in 2 to 2 scattering, what we're going to do is work out the square of the amplitude here and get it into sort of the nicest form as possible, and that's going to require a little bit of work. So thinking about the amplitude, it's a complex number, so to obtain its magnitude, its square, we're going to multiply it by its complex conjugate. However, instead of using the complex conjugate operation, I'm actually going to write this as a Hermitian conjugate, but of course for a single complex number, these two things are equivalent because, a complex number is just a 1 by 1 matrix. And we'll see why we're doing this in a second. It will basically just make our calculation a little bit easier. So doing this, what do we get? Well, we get this e to the 4 over t squared factor. Of course, that just comes from the ie squared over t multiplied by its complex conjugate. And then we get this string of sort of products of spinors and gamma matrices. And this is what we're going to work to simplify in the following steps. So we're going to need to use some of these identities here. So the first one is essentially the defining sort of equation for the Clifford algebra. So it's the anti-commutator of these two gamma matrices is given by this expression here. So 2 times the components of the metric times the 4 by 4 identity matrix, because remember, these are still matrices for each value of mu and nu. So if you're not familiar with what the anti-commutator is, right, the anti-commutator of A and B is just given by AB plus B times A. So we're going to use this expression to go ahead and work out some nice facts about our gamma matrices. Now, before we go ahead and do this, I thought that I'd quickly make a few comments about the actual form of the squared amplitude, just in case anybody had any sort of questions or queries about these. So the first thing you'll notice is that on our gamma matrices, in the term that comes from the conjugate amplitude, okay, so the the Hermitian conjugate, complex conjugate of the amplitude, you'll see we have different spacetime indices on the gamma matrices. This is a crucial sort of thing that you need to do because obviously we cannot use the same repeated indices in the same expression, right? So because we have a repeated index nu here, so we're summing over this index nu, we need to use a different repeated index on these gamma matrices. So that's important. You then might ask, well, why do I have the same spin labels in the conjugate expression? Well, this is because these are really not indices in the same sense of the spacetime indices. You can also think of it, sometimes people like to write the spinors as an actual sort of maybe more function type notation like this, right? So and then you can think of if I squared this, so if I sort of wanted to work out what this was, then this would be something like u star p prime s prime u p prime s prime. So I'd use the same indices, the same sort of labels for those quantities, but it is important to make sure that you use the different labels or different indices, for the spacetime indices when you're squaring an amplitude like this if they're repeated. And the next thing I wanted to say is that these two relationships here, they are essentially normalizations that you can impose on the Clifford algebra basis elements, so the gamma matrices. Now, this is not something that has to be done, but it can always be done. Okay, so we can always make sure that the 0th gamma matrix is Hermitian, and basically from this we can then derive this relationship here. So just again wanted to mention that so that that this is kind of really not it doesn't always have to be the case, but we can always make it the case if we want to. So using the defining property of the Clifford algebra that we're interested in, so this here, so the commutation or the anti-commutation relation, if we set mu equal to nu equal to 0, we can derive a useful property that we're going to use in what follows. So doing this, what do we have? Well, plugging this into the formula for the anti-commutator, we have gamma 0 times gamma 0, so we have gamma 0 squared on the left hand side plus another gamma 0 squared because we have gamma 0 times gamma 0 again, even though they're in the opposite order, right? It's the same object. So we get a 2 gamma 0 squared on the left hand side is equal to, and then we have 2 times eta 0 0, but eta 0 0 in our convention is just plus 1, right? So we're using the plus minus 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 signature. So we have 2 times plus 1, so 2, and then times 4 by 4 identity matrix. So dividing by the 2, we can see that essentially the 0th gamma matrix squares to the 4 by 4 identity matrix, which is nice. So we're going to use this property in what follows. So now we're going to derive a useful result for what happens when you take the Hermitian conjugate of a particular product of spinors and gamma matrices. So one that looks like this. So this is the first term in the conjugate of the amplitude that we have here. Now remember, we showed and we argued, and it's easy to see this in the last video, that this particular sort of product of spinors and gamma matrices is just a complex number. So taking the Hermitian conjugate and the complex conjugate again, are going to give the same overall result. However, when we view this in terms of taking the Hermitian conjugate and we view what's inside the bracket as essentially a matrix product, right? So thinking of, this is like a 1x4 matrix, this is like a 4x1 matrix, and this a 4x4 matrix. We need to remember how we take the Hermitian conjugate of such a product of matrices. So we're going to reverse the order of the product and then take the Hermitian conjugate of each sort of individual object within the brackets. But firstly, we need to remember what the U-bar spinor actually is. Remember, this is the Dirac adjoint, and we defined this in the previous video. So it's just the adjoint spinor, so U dagger, so the Hermitian conjugate spinor, multiplied from the right by a gamma 0. Okay, and then I just still have my gamma mu and my U of P here. So when I take the Hermitian conjugate of this product, again, I'm going to reverse the order and then Hermitian conjugate each object individually. So reversing the order, well, the U-P spinor now comes on the left, but I have a Hermitian conjugate sort of acting on this spinor. So I have U dagger of P. I then have my gamma mu, but I have this, again, Hermitian conjugated. I would then have gamma 0 Hermitian conjugated, but remember, we said that you can always make it such that the 0th gamma matrix is Hermitian. So then I have a gamma 0 here, and then finally the Hermitian conjugate of the Hermitian conjugate, right? That just gives me back the original spinor, so I have U of P prime here. So at this point, we want to turn this into something that looks like, very similar to the the U bar gamma mu U expression we started with, right? I don't want to have these Hermitian conjugates floating around. So how do we do this? Well, the first thing we do is remember a particularly useful result that we just showed, and that is that the gamma 0 matrix squares to the 4x4 identity. So we know that gamma 0 squared is I4. So what that means is that I can insert gamma 0, right, a product of two gamma 0s in here without changing the expression. So let's see what happens when we do this. So we have U dagger P, gamma 0, gamma 0, gamma mu dagger, gamma 0, U, P prime. So now this is precisely our Dirac adjoint spinor here. So this is U bar P. And now what we have here is a gamma mu dagger sandwiched between two gamma 0s. So if we look at this expression over here, so I'll just erase this, we can see that if we take the Hermitian conjugate of both sides, remember on the right hand side it's going to reverse the product, but it's symmetric product in that sense. And the gamma 0s are Hermitian. So if we do this, this tells us that gamma mu is equal to gamma 0, gamma mu dagger, gamma 0. So actually, we can replace this gamma 0, gamma mu dagger, gamma 0 with just a gamma mu. So overall, what do we end up with? We end up with a U bar P, then we have a gamma mu, and then we have a U of P prime. So essentially you can see that what's happening is that when we take the Hermitian conjugate of such a term like this, essentially we basically just swap these spinors over, right? So the one that has a argument of P, or is the spinor with momentum P, goes on the left, the spinor with momentum P prime goes on the right, and then the bars also sort of swap, right? So then I have a U bar P here and a U bar P prime. So that's a useful thing to remember. Make sure you go through this kind of argument once, and once you've seen it once, you can just use this anytime you're calculating these amplitudes. So you can see what we've done now is use the result we just derived to write this product here as this product here, and this product here as this product here. And at the same time, we've actually moved the relative positions of these products around. And remember, that's fine because each of these sort of products here, so where we have something like U bar gamma U, that on its own is a complex number. So I can just pick that up and move that around. So what I've done is I've actually moved this product and placed it here in the respective order. So you can see now what we have is we've kind of grouped them together. So we have the products that involve P's and P primes and the products that involve Q's and Q primes together. So the next step is a crucial step in all amplitude calculations, and it's going to allow us to simplify what follows very nicely. So we're going to rewrite this entire product of spinors and gamma matrices in terms of products of traces of matrices. And the way to sort of get your head around this is, again, this entire product that we have is just a complex number, okay? So by some sort of manipulations that we're going to go through, we can re-express this complex number, which at the moment is being generated by, you know, a bunch of terms that look like something like a 1x4 spinner multiplying a 4x4 matrix multiplying a 4x1 spinner. So that generates a complex number, and we're going to re-express this such that we are getting the same complex number, of course, but we're expressing how we obtain this complex number in terms of traces or products of traces of particular matrices. And this is useful because there are a bunch of identities about traces of gamma matrices that are going to simplify the calculation going forward. So we're going to take it slow. This can be quite confusing the first time you see it. And again, you don't have to do it in this much rigor and sort of this as many steps I'm about to. Every time you do this, you will get used to it eventually, but it's, I think, useful to see it done very slowly, very carefully the first time you know, you come across this, or if you find this confusing. So we're going to go ahead and do that now. So in order to show you how we can obtain traces from these products, we're first going to focus on these 6 terms here, so the ones that involve p's and p primes. And what we're going to do is we're going to rewrite and sort of put back in the spinor indices that we've been suppressing this entire time. And we're going to do this in a way, of course, that is consistent with the sort of, you know, column vector matrix multiplication that's going on here behind the scenes within these spinors and these gamma matrices. So again, I'm going to assume that you've had some sort of exposure to this, but let's just focus on the first 3 terms and see how to do this. So of course, you know, this u bar sp, it is a 1x4 row vector. And then, you know, this is multiplying with the gamma matrix, which is a 4x4 matrix, which is multiplying the 4x1 column vector spinor u s prime p prime. So in index notation, we can do this as follows. So I'm going to write out, you know, it's going to look a bit ugly, and this is why we sort of, you know, tend to suppress these spinor indices in the first place. So I have u bar s p, and then I'm going to put some index, which is going to indicate, you know, the entry of the row spinor. So let's just call this A. Now, this is then multiplying a gamma matrix, which is a 4x4 matrix. So we have gamma mu, and I'm going to put a pair of indices, which is going to be like the row and the column index. And then to represent matrix multiplication, where we have the sort of row vector, if you like, on the left and the matrix on the right, what has to happen is I have to sum over this index here. Okay, so that's what I'm doing here by matching these indices up to be the same. First things first, any repeated indices with the spinor indices, whether they're down or up, means they're going to be summed over. This is because for spinors, we're not going to make any distinction about indices that are up or down. Essentially, that's because the metric is proportional to the identity, essentially. So this means that we're summing over, you know, the index A here. Now, if you don't understand how this sort of index matrix multiplication sort of works, just convince yourself by sort of writing out an explicit example, something like, you know, u1, u2, and then maybe a 2x2 matrix, right? So something like a11, a12, a21, a22, and actually do the multiplication and see that what you end up doing is, you know, summing over the indices in this particular way. So then we need another index for our gamma matrix. So let's just call it B. Ooh, wrong pen. And then, of course, this is multiplying the column spinor. So yeah, this is our u s prime p prime, and then I'm going to write the component of this as b. And again, it has to match up in order to give me the correct sort of, you know, index form of the matrix multiplication with this spinor that's going on. So that's how we do this for the first sort of 3 terms in that product. I'm then going to repeat this, and then we'll go from there. So you can see that what I've done is now rewritten this first product of the 6 spinors and gamma matrices explicitly in terms of the spinor indices and the matrix multiplication that is, you know, consistent with the indices and the positioning of the indices. So again, you should really think of these 2 things as 2 separate products right now. Okay, so we have sort of one product here and one product here, and again, that's encoded in how these indices are set up and how, you know, they're sort of being summed over sort of with one another. But now, because I've written everything explicitly in terms of spinor indices, these are now just numbers, okay? So they no longer have any sort of, you know, matrix or vector structure. So I can actually just pick these things up and move them around completely freely, right? So again, you know, they are just numbers, okay? So for each value of, you know, C or C and D or whatever, they're just a number. So just like when we have the metric written out in terms of something like eta mu nu, that is no longer a matrix, it's representing the component of a matrix, so we can just move it around. So what we're going to do is we're going to rearrange all of these different sort of explicit components where we have the spinor indices showing explicitly, and we're going to rearrange these, and I'm going to group all of the spinors together that have the same spin label and momentum, and I'm going to place the unbarred spinors to the left. And this sounds very strange and very random, but this will become clear very soon as to why I'm doing this. So what that means is I'm going to, for example, pick up this spinor and I'm going to move it to the left-hand side of this spinor. And then you'll see that these two spinors in the middle, they're already in that configuration. So they group together, they both have a momentum P prime and spin label S prime, and the unbarred spinor is on the left-hand side of the barred spinor. So I'm going to go ahead and now rewrite this. So now we've shuffled everything around to have the expression in this form. We can notice something interesting. So if we focus on these first two terms here, again, if we think about this in our heads as having a now column vector on the left and a row vector on the right, this is the expression for the outer product of those two objects in terms of indices. So when you have the outer product of a column vector and a row vector like this, it generates a matrix. Okay, so it generates in this case a 4x4 matrix where the entries are given by just setting, there's no sum here anymore because they're not repeated indices. So I generate the entries in the matrix just by picking different values of D and A. So for example, if I set D equal to 0 and A equal to 0, that gives me the 0, 0 entry. Or if you like, start with 1, so D is equal to 1 and A is equal to 1, that gives me the 1, 1 entry of this matrix, etc., etc. So this is the index form representation of the outer product of these two vectors. So this is just some matrix. Okay, so what I'm going to do is I'm just going to define this to be some matrix, or the components of some matrix. I'm going to call it, let's just call it A, dA. And I can do the same thing for this sort of outer product of these spinors here. Let's just call this B, BC. And then I can go ahead and rewrite this entire expression again. So now I have this equal to A, dA. I have my gamma matrix with indices AB. I then have my other matrix that I've just defined, or the components of that matrix with indices BC. And then finally I have my final gamma matrix with indices CD. Now you can see, again, in terms of indices, what is this representing? Well, it's firstly a matrix product. So, I'm multiplying this column sort of row like this, like matrix multiplication. Again, another set of matrix multiplication here and here. So here and here. And then another set of matrix multiplication here and here. So I'm multiplying these four matrices together. So again, I can just express this as a single matrix, right? Because I multiply four 4x4 matrices together, I'm going to get a single matrix. So let's just call this C. And what are the indices for this matrix? Well, the indices are, the three indices that are not summed over, that are left, sort of, I guess, either side of this sum, right? So, this D here is not being sort of multiplied with a row or column of any of these matrices. So that means that this product can be written as some matrix C, and the indices, well, they're D, right? Because all of these ones are kind of in the middle, and they're, giving me the matrix multiplication. But this here is precisely sort of what you would use to represent the trace of some matrix, right? So I'm summing over its own sort of, diagonal elements, right? So 1, 1, 2, 2, 3, 3, 4, 4, right? That is the trace of some matrix. So I can say that this is the trace of some matrix C. So actually what we've done is we've re-expressed this entire product by examining it and moving things around in looking at the sort of multiplication in index form. And if you're not familiar with how multiplication of indices works, so if you haven't done a lot of differential geometry, which is really where I picked up this skill, then this might be a little bit confusing. But hopefully to those of you who have seen this, you can sort of follow along and see how this generates a matrix trace. So basically the big idea from this is that we can indeed express this as a trace of some matrices. Now, what are those matrices? Here I just called them, all of these different, A, B, C, and D. But we can just literally express them. Now, dropping the spinor indices, they've served their purpose to help us analyze this and see that we can express this as a trace. So really, I'm now going to drop these spinor indices and rewrite this in the following way. So this is the trace, And again, I'm going to write it in terms of the outer product of these spinners. So it's USP, and then we had U bar SP. I had a gamma mu. I had then my other spinner outer product, so U S prime P prime, U bar S prime P prime, and finally the final gamma matrix, gamma nu. So this is the trace that we can sort of recast our complex number that the product of these 6 spinners and gamma matrices is equal to. We can recast it into this trace here. So hopefully that was clear. And then what we're going to do is eventually we're going to be using something called spin sum. So we're going to be summing over and averaging over the spin states, and then we can turn this into an even nicer expression. So repeating the exact steps we've just done, but for the remaining product of the 6 spinners and gamma matrices that involved the momenta Q and Q prime and the spin labels R and R prime, you'll see that we obtained this expression here. So the product of 2 traces, and I do encourage you to pause the video and just make sure you can obtain this trace in exactly the same manner that we just did. Again, you only have to do this really in so much detail once or twice. Eventually you'll be able to spot, how to sort of go from here to get these traces. I also wanted to mention as well, I think I was missing a prime from both of these labels in the previous sections of the video, so I do apologize. It was just a typo, so hopefully that didn't cause too much confusion for people watching. But we sort of done what we set out to achieve. And we've now expressed, this amplitude squared in terms of a product of 2 traces. And again, I think I might have sort of, again, misspoke and was talking about, this thing being, this entire thing being a complex number. But of course, individually these amplitudes and its Hermitian conjugate complex numbers. But obviously when we, take the amplitude squared, of course, we get a real number. So, you can sort of think of each of these blocks as being a complex number. But obviously together they must give a real number. But the nice thing is that we've now expressed this real number, which is our amplitude squared, in terms of the product of 2 traces. And this is going to allow us to use some nice trace identities that come along with gamma matrices, which are going to simplify the calculation. But before we go ahead and do this, we need to discuss something called spin sums, and we need to sort of see why we even introduce summing over these spin states in the first place. So typically when experimentalists measure something like a differential cross-section, the beams of particles that they fire at one another are unpolarized. So what this means is that they have no control, or they're not controlling the incoming spin states of the particles in the beams. And therefore, to account for this in our calculation of the differential cross-section, we need to average over the incoming spins of the particles. So in our case, we have an electron and a muon incoming. Each of these have 2 spin states, 2 possible spin states, right? So spin up and spin down along some sort of particular axis orientation. So we need to account for that basically with a factor of 1/4 and then sum over those initial spin states. But we're not done yet. We also have to sum over all possible final spin states as well, because we allow for any final spin state to sort of contribute, within the experiment. So essentially what we're going to have is overall a sum over all of these spin indices, so S, S prime, R and R prime. So the S and R are the incoming ones, and we're summing over them, but then we're dividing by, in this case, a factor of 4 to account for the 4 total possible spin states, 2 for the electron and 2 for the muon. And then we're also summing over S prime and R prime. Those are the outgoing spin states, and again, that's to allow for any possible final spin states of those particles outgoing. So overall, we're going to have the following. So this is the relevant object that we're going to need to calculate for our differential cross-section. So notice again, it has the sum over these 4 spin labels here. And we also have this quarter, like I said, that is just to reflect us averaging over S and R, so the 2 incoming spin states for each particle. And sometimes you'll see people write this as the sum over spins. In fact, I normally do this anyway, and I probably will do this at some point in the video. It's just to save people writing out all of those 4 spin labels every time. So to make our life easier, and in fact this will make the traces easier, so evaluating these traces a lot easier, we're going to use the following identity over here. So essentially it's an identity for the outer product we spoke about. Okay, so you can see we have such outer products here, but it's not just the outer product on its own. It actually requires the spin sum, okay, so the sum over the spins, in order to sort of use this identity. So this identity is normalization dependent, so it depends on how you normalize the spinners. So in our normalization, which I'm not going to really go into too much detail, it doesn't really matter. The idea is that we can basically express the outer product plus the sum over the spins as p slash plus m. So I'm going to talk about this quickly and what this means. So this slash, this is due to Feynman, I believe. So this slash notation just means that you're contracting whatever object with a gamma matrix. Okay, so in the case of p slash, that means we have gamma mu and p mu. So we're contracting the indices there. Now note this is a 4x4 matrix, as you would expect, right? We said this was an outer product, so it's a 4x4 matrix. So here we're actually technically suppressing, an I4 as well, so a 4x4 identity matrix. But again, just know that it is there. So this sum over spins, again, that's why it's nice that we introduce this, because we can actually express all of these outer products once we, include this spin sum, which is what we need anyway for the differential cross section. All of these outer products are going to basically become, p slash plus m. Now, obviously, we need to be careful and pay attention, which spinors relate to which, so which momenta relate to which particles. So we're going to have a mass of the electron for the, these spinors here, which, all have the momenta relating to the electrons. If you go back to the Feynman diagram, and these are going to have, a mass of the muon in them. So let's go ahead and do this now. So you can see that upon using these spin sum identities, the sum over the final and average over the initial spin states of our amplitude squared has now become this expression here. So we've just replaced all of those outer products again once we have summed over all of those spin labels with p slash plus me or q slash plus mu, etc. So what we're going to do now is something which is often called traceology. The idea is that we're going to use a bunch of trace identities for gamma matrices to simplify these traces, down into sort of neater sort of products. So let's focus on this first trace. Okay, so this trace here. So obviously we can, expand everything out inside the trace, and we can use the fact that the trace is linear to split this up into 4 different traces. And then we can work on each of these traces separately, and we're going to use these 3 identities here to help us. Okay, so these are going to be the 3 most important. There's a bunch more. If you go on to do electroweak stuff, there is identities involving gamma 5. So if you don't know what gamma 5 is, don't worry. It's related to chirality, but the idea is that these identities are going to help us sort of go ahead and simplify everything down nicely. So the first thing, kind of one of the key ones to remember, is that the trace of any number of odd gamma matrices will give us 0. So that's going to be very useful. It's going to simplify many of these traces straight away. The next is that if we have the trace of 2 gamma matrices, this is 4 times the metric components. And again, you'll see the indices match as they appear. But of course, this is symmetric, right? So it doesn't matter which order you put them necessarily. And then here, this is one where you do have to be careful about the index positions. The trace of 4 gamma matrices, and then you can see it's given by this strange expression here. So this might look a little bit complicated. The way I like to remember this final expression is, you have the first, it's always sort of 2 products of 2 metric components. So the first one you have, if you like, I like to label the indices. So 1, 2, 3, 4. So in my head, I always think 1, 2, 3, 4 minus 1, 3, 2, 4 plus 1, 4, 2, 3. I don't know, that might just be me being weird, but that's a nice way to remember sort of, the direction of the indices in relation to how they appear in the trace. Let's go ahead and use these identities to actually simplify some of these traces. So let's start from sort of, easiest and then go to the harder ones. So the first one we're going to start with, let's say, is this one here. So let's think about rewriting this trace. So what I want to do is I'm going to expose the gamma matrix structure explicitly. So remember, p slash is actually equal to gamma mu p mu, right? But I have to use a different index here because I already have a mu here. So let's use, for example, rho. So this trace star, again, so we're trying to expose that gamma matrix structure. Now, one thing to note is that I want to always, be writing everything with all of the gamma matrix indices either up or down. So what I'm actually going to do is I'm going to have the index on p raised, and then the index on the gamma matrix down when I'm sort of getting rid of this p slash for a p and a gamma contracted. So that's just a nice thing to always do. So make sure you always have the indices of the gammas in a trace either all up or all down. You don't have to, but I think it is just the easiest way to do things. So what we're going to do is we're going to write this in the following way. So we're going to say the trace of, and then again I said I'm going to have this up and use the index rho, so p rho, and then I have gamma rho, gamma mu, me, gamma nu. Now, obviously the interesting thing about the trace, like I said, is it's linear. So that means that we can actually pull these factors out. So remember, don't get confused by the fact this carries an index. For each value of row, this is just a number. So we can pull components of 4 vectors, or even whatever metric components out of a trace. So that's completely fine. So rewriting this again, we have p row me, and then we have the trace of gamma row, gamma mu, gamma nu. But one of our identities says that the trace of any odd number of gamma matrices is 0. So this just vanishes. So this trace actually just gives 0. And similarly, you'll see that this trace here, also once we repeat a similar process, so I urge you to pause the video and have a go yourself, you'll get to something like this. So this also is a trace of an odd number of gamma matrices. So this also gives 0, right? So we can ignore these two traces straight away. Okay, so that's why the beauty of summing over these spins and doing this whole manipulation to start off with, it seemed a bit pointless. But now the power of doing this sort of whole manipulation really comes into play. So now let's focus on this trace here. So again, this one's rather nice. So let's just put a double star here. So this final trace, or second to last trace, we have the following. Well, you can see straight away actually that I can just pull out, again, like we said, because the trace is linear, these two factors of me. Of course, that's going to give me an me squared. And then this is multiplying the trace of gamma mu, gamma nu. And again, using this identity here, of course, it holds for both indices down as well. This is going to be equal to 4 me squared, and then times, the metric components, eta mu nu. So that one's quite nice as well, pretty easy to simplify. So for the final trace, we have to be a little bit more careful. So it's a little bit trickier to work out. So we're going to do the same thing. We're going to expose the gamma matrix structure. So I'm going to rewrite it to start off with as the trace of, and then again, we want to keep all of the indices on the gamma matrix or gamma matrices down. So I'm going to call one of them, for example, p alpha. And I'm contracting this with gamma alpha. Okay, so again, that's just replacing or turning the slash into a contraction of, p alpha and gamma alpha. Then we have a gamma mu. Then we have, again, going to expose the gamma matrix structure. So I'm going to call this, for example, p prime beta. And then I have a gamma beta, and then a gamma nu on the end. So again, these are just numbers, so I can pull them out of the trace as the trace is linear. So pulling them out, what do I have? I have p alpha, p prime beta, and then the trace of gamma alpha, gamma mu, gamma beta, and then gamma nu. And now I can use this identity. Again, it holds all of the indices down. So like I said, you can just read off the identity carefully, but you will sort of see how you can do this quite quickly if you try and at least learn the trick that I kind of said, or at least that's a good way of remembering it. So you have 4 p alpha, p prime beta, and then again we're going to have so write this out everything carefully. So we have eta alpha mu, eta beta nu, minus eta alpha beta eta mu nu, plus eta alpha nu, and then eta u beta. So just sort of basically check and go along, right? So make sure the indices correspond to the positions that they should. So of course we have different indices here, but you just need to try and spot them and see how the indices you have link to the general formula. But again, it's good maybe just to label them like I said. So now the interesting thing is that we can multiply in obviously by these 4 components, these 4 vector components. So for example, when I have something like with the first one, eta alpha mu, eta beta nu, right? And then I multiply this by p alpha, p prime beta. What do I get? Well, again, I'm assuming that you're sort of familiar with special relativity. So over here, I'm going to lower this index alpha. So that's going to give me the following. That's going to give me p mu. And then over here, I'm going to lower in this index beta, and it's going to become a nu. So I get a p prime nu. And I'm just going to repeat this for all of the other products. So I'm going to multiply these things in. So if you go ahead and do this, you'll obtain this expression here. So so all I've done is brought the product of these two things with this pair of metrics to the front here. So it's actually very similar. It's just that the indices are swapped around. And one thing you will note is that when we again multiply this pair of 4 vector components, 4 momentum components with this term in the middle, you'll see that the indices on the metric are such that we're actually going to contract the indices on these two terms here. So what happens is we have the eta alpha beta. You can either lower either index, but let's say we lower the alpha index on the p. We have something like p beta, p prime beta, but we're just going to write this and express this as the 4 dot product, right? So that's just going to be p dot p prime. And again, in our metric signature, this is essentially just going to be the product of the 0 components of these vectors, so p0, p prime 0, and then we're going to minus the, because again, this comes from the plus minus minus signature, the product of the the Euclidean part, right? The sort of i's, so 1, 2, 3 of these two 4 vectors. So once we've done that, this is the final expression for that trace. So we now have 2 non-zero traces after all of this work. We have this trace we just worked out, and we had the 4me squared e to mu nu. So let's see how we can tidy everything up and go from there. So repeating the computation for the second trace as we just did, it's pretty much exactly the same. So again, I encourage you to pause the video and have a go yourself. The only difference is the indices are upstairs in this second trace, but you can see the structure is exactly the same. But doing that, you should end up with this expression here. And you can see that we factored out a factor of 4 from both of those trace expressions. So that's given us an overall 16. So now we have a 4 sitting up here. And one interesting thing to note is that, you can see kind of how the index or the spacetime index structure has carried through. So before in this trace, we had, a mu and a nu downstairs. We still have, 4 separate terms, but each of them still have 2 mu and nu indices. But of course, they're not free because they are contracted over here. But again, you see the same thing happening, right? Each term. And this, I guess, potentially looks confusing, so that's my bad. That is the mass of the muon, not an index. But these indices on the gamma matrices, you can see they have mu and nu upstairs, and each term in here has a mu and nu upstairs. So that's something to sort of, give you a hint that you're potentially on the right track at least, right? If that's gone wrong, then you sort of know the space-time index structure has gone wrong somewhere, and you've made some sort of a typo. So from this point here, we could just go ahead and multiply these 2 products together straight away, but we can simplify things a little bit just to make it somewhat nicer. So rather than having to multiply 2 brackets containing 4 terms each together, we can actually just expand 2 brackets that contain 3 terms each. So the way we're going to do this is return to our original Feynman diagram, and I'm going to draw it very roughly, again, not worrying about the photon. I'm just going to sort of think about it in terms of momenta. So we had a momentum P going here, a momentum P prime going out here, and a momentum Q coming in here, and a Q prime going out here. So remember, we showed that, by thinking about conservation of momentum, so momentum in equals momentum out at each vertex, that we have some momentum flowing down here, that's equal to P minus P prime. By a similar argument, you can also show that, this is also equal to, so again, we think at this vertex here, we've got K going in and Q going in, and that's equal to Q prime. So K is also equal to Q prime minus Q. And we said the square of this momentum, that kind of defines the topology of this diagram. So that's a T-channel diagram. So we defined T to be equal to P minus P prime all squared, which is of course equal to Q prime minus Q all squared. And if we work on this first term here, we can see where we get a P times a P, which is a P squared. And then we have, 2 lots of P dot P. So again, these are 4 vectors now, and I'm sort of suppressing the space-time indices in here. So we have, P times P prime is really P dot P prime, where the dot product again is that, 4 dot product. So again, from special relativity, so we have a 2 P dot P prime, and then we have a plus P prime squared. Now, if you remember, these external particles, they are on shell, which means they satisfy the relationship that is P squared is equal to M squared, again, if we've set C and H bar to 1. So what that means is that this is actually an ME squared here, and ME squared here, and therefore this is actually equal to 2ME squared minus 2p dot p prime. Now you might ask why this is useful. Well, you can see that we can actually then sort of match up this expression to something that looks very similar in our trace terms. So we have a p dot p prime and an me squared, but both of these are multiplying a copy of the metric. And so if we divide by a factor of 2 and multiply by the metric components either side, you can see that we get the following. We have a half t eta mu nu is equal to me squared eta mu nu minus p dot p prime eta mu nu. So sorry, I'm just trying to squeeze it in here. And so we can replace these two terms here with a 1/2 t eta mu nu. And because this is also equal to q prime minus q all squared, we can do a similar manipulation over here. And I do apologize. I probably should have just used two different sort of letters, one big M and one small m for the masses. But again, that is, if you see a mu on an m, that is not a space-time index. But I can repeat something similar. So again, pause video, have a go yourself, see if you can get to something similar. And you'll see that this is going to be a sort of similar manipulation, but I can replace this with a 1/2 t eta mu nu as well. Okay, and again, that's just by this relationship here. So I believe I just misspoke a little bit there. So obviously for these two terms here, we're going to replace this with a t over 2 and then, the metric, but with components upstairs. And of course, that's because, in order to get the expression to match, we need to multiply with the metric upstairs. But hopefully you did it yourself and, that wasn't too much of an issue. It was pretty clear what was going on. So now at this point, we have nothing else to do but expand, this pair of brackets and multiply everything out. So I'll do the first couple terms with you just to sort of show you how it goes. So we've got this, this pair of four momentum components, and we're going to multiply it by these. So really what's going to happen is you're going to have the indices just contracting and giving you some 4 dot products, right? So here we've got a p mu and a q mu. So that's going to give me a p dot q. So let's write this out. So 4e squared, sorry, 4e to the 4 over t squared. And then I have, so yeah, p dot q. So you just got to pay attention to which indices have been contracted together. And then I have a p prime contracting with a q prime, so that's a p prime dot q prime. And with a lot of this stuff, you will just kind of see these things a lot more quickly. Even with the trace stuff we've just done, eventually you'll be able to look at this and kind of just simplify things very quickly. And a lot of the same sort of structures and patterns appear in a lot of these calculations, so you won't have to do everything as sort of tediously and break it down as much as I am, but I think it's good to do this when you first see it, because some of it can be quite confusing. I know I found it quite confusing, a lot of this when I first found it, so I kind of broke it down and did it slowly. So I wanted to do an example doing that, but it does get quicker, don't worry. So here you can see, again, just pay attention to which indices are going to contract. So we have a p and a q prime, so p dot q prime, those indices contracting, and then this is multiplying a p prime dot q. Again, that's this term with this term. And again, I'm just writing these things multiplied next to each other because they're just some numbers. And then finally, we have this term and this term over here. So again, this metric is just going to contract those indices. So I'm going to have, a p dot p prime multiplying a t over 2. So plus t over 2 p dot p prime. And then I'll let you have a go and do the rest of these, yourself and simplify and collect everything. But here, I just wanted to point out something to watch out for. So we have t over 2 times t over 2, that's fine, that's t squared over 4. But something you may or may not be familiar with is when you have the metric sort of contracting with itself like this. Now there's a general identity that says the following. So if I have something like eta mu alpha, eta alpha beta, then this is going to be given by the Kronecker delta with the indices to sort of, match up with this. And this is basically just the index version of this statement, right? That the metric times its inverse is equal to the identity. However, in the situation where, this index, or, all of the indices are the same, we basically have delta mu or something like this. And if you think about this, we're summing over, these indices here. Of course, they each take the value of 1. So this is just, in general, it's the dimension of the space-time. But of course, in here, that's just going to be 4. So actually, this just gives you a t squared over 4 times 4. So you just get t squared for that term. So pause video, have a go, multiply it out, and I will show the result now. And so once you expand everything out and tidy it up, this is the expression that you should end up with And it's very nice. You can see that we're going through this effort, but we are slowly breaking this down into simpler and simpler looking sort of terms, and it's going to get even simpler still. But up until this point, we've been working completely generally, sort of valid for any situation. From now on, what we're going to do is we're going to go ahead and start considering the higher energy limit of this scattering process. Now, this is something which is done all the time. It makes things a lot simpler. You don't have to do this, but it means we can start to neglect certain terms. And then this is going to really start to tidy up this sort of spin summed average amplitude squared a lot. And again, in practice, this is really going to be a true reflection of reality. We're not going to be throwing too much sort of, information when we do this. But you don't have to do this, but we are going to do this. And we're going to look at that a little bit now and explain it first, and then we'll go ahead and simplify this expression even further. So despite there only being one valid Feynman diagram at tree level for the process that we're interested in here, so that was a T-channel diagram, that doesn't stop us thinking about, what the other diagrams would look like purely just in terms of momentum flow, so that we can construct relationships between, some of these dot products of momenta in terms of the other Mandelstam invariants, S and U, that we don't have appearing here naturally. And this is perfectly fine to do. Just because we don't have an S and U channel diagram, we can still express some of these dot products in relation to, S and U. And this is going to, again, simplify our expression. And also is going to be really useful in the high energy approximation. This is where the simplification is really going to come in. So let's think about what the S channel diagram would look like. So it would look something like this. And we would have, of course, we fixed our momenta, sort of, the respective positions. So we had a P and a Q here. These were both going into this vertex here. And then we have a P prime going out here and a Q prime going out here. So that means, again, by conservation of momentum, we must have P plus Q flowing through here. Remember, in the S channel diagram, the momentum that flows through the internal line, the square of this is what defines S. So, in this particular problem, how we've labeled everything up, S is going to be given by P plus Q all squared. But of course, by conservation of momentum at this vertex, P plus Q must equal to P prime plus Q prime. So this is also equal to P prime plus Q prime all squared. So here's where we're going to actually start looking at this high energy approximation. So let's just take, for example, P plus Q all squared. So when I square this, what do I get? Well, of course, I have P squared plus 2P dot Q. So again, this is, this dot here is, the 4 dot product, and the P squared, is P mu, etc. So again, this is just stuff from special relativity that hopefully you're familiar with. And then we have a Q squared here. So remember, these external particles, they are on shell. So what this means is they satisfy the relationship P squared is equal to M squared. Again, we've set H bar and C equal to 1. I've probably said this a few times throughout the video. So, we can actually replace these here in terms of the masses of the respective particles. So the P relates to an electron and the Q relates to a muon. So this is going to be me squared plus 2p dot q plus mu squared. Now, the high energy limit essentially allows us to ignore these mass terms in comparison to this 4 dot product here. So what we're going to eventually say is that S is, approximately given by 2p dot q in the high energy limit. So let's try and see why this actually makes sense quickly. So again, thinking sort of in terms of special relativity, we can write the form momenta of these particles in the following way. So I'm going to write it in kind of like a column vector notation. So, for the first component, that's going to be the energy of the particle. And then we're going to have some momentum P here. So that's for the electron. And then again, we have, the energy, which depends on the 3 momentum, and then, the 3 momentum as the other components. So when I take this 4 dot product, what do I get? So again, because of the sign of my metric, I'm going to have, well, first I've got EP times EQ, and then I have minus P dot Q. But of course I can replace this, with the magnitude of P times the magnitude of Q times the cosine of theta, where, theta is the angle between these two 3 momenta. So now we can think back to, again, something from special relativity, which is the relativistic dispersion relation, which essentially says that, EP is equal to the square root of P squared plus M squared. So in this case, that'd be ME squared. And when something's moving in the high energy limit, we assume it's moving relativistically, which means that, its free momentum squared, the magnitude of its free momentum squared, is going to be much greater than its rest mass energy squared. Okay, so its kinetic energy is essentially much greater than its rest mass energy. So we can ignore this mass term here in comparison to the free momentum squared, and we basically have that the energy goes like the magnitude of the momentum. So then this term here actually just becomes the product of the two energies again, but with a cosine theta in between. So we have EP EQ cosine theta. So provided the angle between the two incoming beams is not small, so for example, if they're in a head-on collision, then this cosine theta is going to be -1, right? Because theta would be 180 degrees. Then we're basically going to have these terms here, which are the energy of these particles, which is assumed to be much greater. That's what we mean by the high energy limit, much greater than the rest mass of these particles. So those terms are going to dominate, and therefore in the high energy limit we can neglect these mass terms in comparison to these sort of 4 dot products. So that's going to be very useful. So what that means is that we can replace in the high energy limit, or we have this relationship at least between P dot Q and S, right? And we can also obtain a similar relationship between P prime dot Q prime and S. So you also see that this is the same as 2 P prime dot Q prime because of this up here. Now, if you go ahead and repeat this process for the U-channel diagram, so again, I encourage you to pause the video and have a go at this yourself to see if you can get these relations. But the idea is very similar. So we set up the U-channel diagram that we sort of would have had, which looks something like this. So we have a P prime up here, Q prime here, P, Q, right? These are the momenta going in and out like this. And so again, by conservation of momentum through here, our U-channel momentum is going to be P minus Q prime. That's also going to be the same as P prime minus Q. And you can see that again just by conserving momentum here. So again, we're going to have 2 different relationships that's going to relate U to various dot products of P and Q prime. And you can go through this process, and I'll go ahead and put all of the results that you're going to find on the screen now. So following through with the same logic for the other 2 diagrams, so the U channel, which I said just have a go at, of course you need to do the same thing for the T channel as well. I should have mentioned that. So again, pause the video and have a go if you didn't already, to obtain these relationships between the Mandelstam T and these various dot products in the high energy limit. Again, it's exactly the same, so you just need to again make sure you draw the diagram correctly. So see the first video to make sure you can sort of understand how these sort of different topologies are related to the momentum flowing through the diagrams. Of course, there's always 2 equivalent momenta. You can sort of say that are flowing through there, which gives you 2 different relationships. Then obviously square them, neglect the mass terms, and you'll obtain these relationships between the Mandelstams T and U and the various dot products. So now all we need to do is just use these relationships in this high energy approximation to get rid of all of these dot products in the above expression. So first things first, this here is going to contribute a factor of S. This is going to contribute a factor of S over 2. So it's going to give us an S squared over 2 overall. This is going to give me a factor of minus U. This is going to give me a factor of minus a half U. So that's a plus U squared over 2. This is going to give me a factor of minus a half T. So overall that's a minus a half T squared. And this is also going to give me a factor of minus a half T. That's another minus a half T squared. And this is really where the magic starts to happen, because you can see this, this, and this all cancel out nicely, which is just, really sort of magical to see happen this late in a calculation. Things really start to simplify. Like I said, there was a reason for doing all the work, and this is kind of why. So now we can say that, in this high energy approximation, we have the following. So we can combine these 2 remaining terms now and cancel a factor of 2. So we're going to have a 2e to the 4, and then we're going to have an s squared plus u squared over, not 2, t squared. And that's a remarkably simple expression after all of this work, and this is kind of the reason we do it, like I said. But that's quite nice. I think it's quite a nice answer to get to after all of this work. So what we're going to do now is we've got the piece of the puzzle that really is the most of the work. We're now going to sort of state the differential cross-section formula and basically finish off and tidy this up. So finally, we're in a position to go ahead and state the result for the differential cross-section for 2 to 2 scattering in the center of mass frame. So just note I've introduced some new notation here. So this bar is just basically replacing me having to write the sum over final spins and average over initial spins. And again, this is just the previous result that we had before. So the formula is what it is. Again, it only holds in the center of mass frame. And I'm not going to go ahead and derive it here. I can do that in a separate video if people would like, but if not, you can find derivations of this. I believe in Peskin and Schroeder, and Schwartz has quite a nice derivation as well. It's not too tricky, it's just a bit of a longer kind of derivation. So the only thing I really wanted to talk about here is this factor. So the magnitude of the outgoing through momenta divided by the magnitude of the ingoing through momenta. Now note it doesn't matter which of the two particles you pick for either the ingoing or outgoing momenta to take the magnitude of their through momenta, because of course in the center of mass frame the key thing is that in the incoming frame, of course, the momenta are equal and opposite, and therefore by conservation of momentum, the momenta in the outgoing frame must be equal and opposite. So they're the same in magnitude, just in the opposite direction. But the interesting thing about this factor is that when all of the masses are equal, or in the high energy limit, we don't actually need this factor. So I'm going to go ahead and try and show why we can drop out this factor now. So basically we have four vectors at play here. So four momenta describing this process. So it's kind of doing a bit of relativistic kinematics now. So we have the 4 vector for the electron, so EP and P. We have the 4 vector for the incoming muon, so EQ. Now, the through momentum of the incoming muon, yes, I could label it Q, but of course, in the center of mass frame, it's equal and opposite. Okay, so it's actually going to be given by minus P. And then similarly for the outgoing states, I have the electron, which has energy E, which I'm going to label with P prime. It's momenta, and then again some momentum P prime, and again just in the same way, the muon will have equal and opposite momenta, so we can call this EQ prime, and then obviously the through momentum is going to be minus P prime. So if I focus on firstly the two incoming sort of states here, remember we said at high energies, and we showed how we can get this approximation using the relativistic dispersion relation, that the energy of some particle is approximately equal to the magnitude of its through momentum, okay, because we're neglecting the mass in the energy, the relativistic dispersion relation. But of course, this thing here is telling us that actually, because the magnitude of this through momentum for the muon is going to be the same as the magnitude of the through momentum of the electron, because the minus sign, is just done away with by the absolute value. So actually, this is going to be equal to, the energy of the muon, and therefore I can just say that they share the same energy E. So actually, the two incoming particles have the same energy, and I can play a similar game for the outgoing particle, so EP prime. That's approximately the absolute value. P prime. But of course, this is going to be equal to, because again, they have the same magnitude of the momenta, just in opposite directions. This is going to be equal to EQ prime, so I can just call this E prime. So now, if I think about conservation of energy overall, what do I have? Well, I have that, 2E must be equal to 2E prime. And actually, therefore, that E must be equal to E prime. Okay, so what this is saying is that all of these particles share the exact same energy in the high energy limit, right? This is only valid in the high energy limit. You'll find something similar if they all have the same mass as well. So what does this mean overall? Well, this means, again, essentially energy and mass in this high energy limit energy and momentum are related, or magnitude of through momentum are related. So if I said, okay, well, now I know that all of the energies are just E, so I can just call all of these E. Well, what must their magnitude of their through momentum be? Well, we know that E is equal to the absolute value of P, right? But if they all have energy E, that means they all must have equal absolute values of their through momenta, okay? So not necessarily equal through momenta, right? They can be in different directions, but the magnitude of those vectors must be the same. And again, this just comes from, and again, I really should put an approximation here in the high energy limit, but this means they all have approximately in this high energy limit the same magnitude of their free momenta. So in this limit, this term actually vanishes. So our differential cross section is actually just going to only be, what we just calculated multiplied by this factor here. So let's go ahead and write that down now. And there we have it. This is our expression for the differential cross-section for electron-muon scattering at tree level in quantum electrodynamics, where the differential cross-section is given in the center of mass frame in the high energy limit. So it's a really nice result. It's very simple, which is, kind of why this is such a beautiful calculation to go through. One thing you can do here, you can express this in terms of the fine structure constant. So alpha is e squared over 4 pi. So therefore you can write this as alpha squared over 2, but I just chose to leave it in terms of e and pi's. Now, we're not completely done yet. We could be done. I mean, this is technically a final answer. However, obviously, the differential cross-section, what is it kind of differential in, right? I mean, this is our solid angle here. So, if I wanted to integrate this to find what the full total cross-section was, then I kind of want to expose the angular dependence of this expression on the right-hand side. So I thought we'd quickly take a look at how to do that. So essentially, we're going to basically undo the work we've done with the Mandelstoms and go back to sort of having the scattering angles in there and a tiny little bit more relativistic mechanics. So we'll do that now. So what I've done is I've just rewritten these relationships we derived earlier between the Mandelstam invariants and the various 4 dot products of the four momenta in this high energy limit, because we're going to be using these to extract some angular dependence. And I've also drawn this little sketch, and I think this is something useful to do, anytime you have a problem like this. So, it's basically just showing all of the 3 momenta of the particles in a little sketch. So we have, the electron incoming, the muon incoming, of course, these are equal and opposite. Similarly for the outgoing muon and electron, those are equal and opposite. I've labeled on this angle here as my scattering angle theta. And of course, you can convince yourself that this angle is pi minus theta. So that's going to be helpful when we're analyzing these various Mandelstam invariants. So let's start with S, the first one. So S, as we can see up there, is approximately twice p dot q. So again, thinking in terms of special relativity, I hope you're familiar with, we have this is going to be p0, q0, and then minus, because of my metric convention, my my space components come with a minus sign, and then p dot q, my 3 dot product now. So remember we showed that all of these particles have an energy equal to some energy E, right? It's all the same. So, and remember that the 0th component of your four momenta is precisely your energy. So here I'm going to get a factor of E squared. And remember we also showed that all of these particles have exactly the same magnitude of free momenta, and that was also given by E, right? So that's what we're saying down here. So I can express this in terms of the formula for the 3 dot product. So we're going to have the magnitude of P times the magnitude of Q times the cosine of the angle between them. So that's going to be E squared times the cosine of the angle between them. But for these 3 momenta P and Q, well, that's the incoming momenta, okay, and they're coming in head on, right, in the center of mass frame. So I should have mentioned this drawing is, specifically because now we're in the center of mass frame. So, in that situation, they're coming at each other head on. So the angle between the 2 beams is pi, and cosine of pi is -1. So overall, what do we have? We have 2, and then inside here, we have an E squared, and then we have, an E squared times a -1 times a -1. So that gives me a plus E squared. So overall, this is going to be 4E squared. So that's quite a nice result. I'm going to jot it up here so we've got room to do the others. There's no angular dependence coming in from S, so we don't need to worry about that. But there will be some angular dependence coming in from the other invariants, as we'll see now. So let's have a look at T. So again, T we can see is approximately minus 2p dot q. So again, I'm going to write this out. This is going to be p0, p prime 0, and then minus, and then we're going to have, p dot p prime. So again, they all have the same energy. So all of their, 0 four momentum components are the same. So this is going to be -2. We're going to have an E squared here. And then actually, again, we're going to have a similar sort of structure. So we have, both of the magnitude of these 3 momenta is going to be E squared. So again, we've got magnitude of P times magnitude of P prime. That gives me the E squared. So I've got a minus E squared. And then the cosine of the angle between them, well, I'm actually labeling the scattering angle as just theta now. Okay, so that's bringing in my angular dependence in the variable theta. So I just have a cosine theta here. And therefore, I can factor out a factor of E squared. And so I have -2 E squared 1 minus cosine theta, so you can see some angular dependence creeping in through t. And if I repeat a similar story for u, what do I have? So u is approximately minus 2, and then now it's going to be p0 q prime 0, and then minus p dot q prime. So we now need to come to our diagram. So again, the first part is going to be exactly the same. I've got an e squared here, and then I need to be careful here. So again, I'm going to have an e squared factor, but I need to worry about the signs, because what I'm going to have is, well, I want the angle. Okay, I'm taking the dot product of p and q prime. But if I look at my diagram, that is a relative angle of pi minus theta, right? But cosine of pi minus theta is actually equal to minus cosine theta, right? So so actually, I'm going to pick up an extra minus sign, but I can still re-express this in terms of cosine theta. So what am I going to have? I'm actually going to have a plus. Wrong pen. I'm going to have a plus here, and then I'm going to have an e squared cosine theta. So here, I can factor out an e squared again, and then I have a minus 2 e squared, but then I now have a 1 plus cosine theta for my angular dependence in u. So now we can go ahead and rewrite s squared, u squared, s, and t squared, all of these factors in our cross-section, in terms of their angular dependence and this energy. So if you go ahead and you use the relations we just derived to eliminate s, t, and u from this expression here, you should arrive at this expression. So make sure you pause the video and check that you do get to this same expression as I did. And then from this point, we can actually simplify it a little bit further, because we can remember our half angle formulae. So 1 plus cosine theta, that is going to be given by 2 cos squared theta over 2, and 1 minus cosine theta. And really, this is just tidying things up at this point. 2 sine squared theta over 2. So putting that into here and here, you basically end up getting a 16e to the 4 factor here that you can cancel everywhere, and you'll still have a 4e squared in the denominator. So overall, you are left with this final expression for our differential cross-section, and that is it. Okay, so this is as far as we're going to go. We're not going to do any more simplifications. This is our final answer, which contains all of the angular dependence. So if you wanted to integrate this to obtain the full cross-section, of course, you're going to be integrating over the solid angle. So just to give you a recap of this, obviously this is really going to be integral of your your polar and your azimuthal angles. So we have 0 to 2 pi here. That's just trivial, right? And then you have your integral from 0 to pi d theta. Sometimes you'll see this particular integral often in these contexts as well, because we have this trig function dependence. Sometimes you'll see it rewritten as the integral from minus 1 to 1 d cos theta. That is just essentially just a change of variables, right, to get it to this form. So that's it. So I hope this video was helpful. I appreciate it's a long video, but I wanted to take it slow and go through all of the steps in detail. But as always, thank you for watching. And if you have any questions, then please do let me know in the comments.